Okay, well, thank you very much, Paul. First of all, for the invitation to come here and for the introduction, and thank you for everybody who's turned out. The subject I'm going to address tonight is the quest for life in the universe. And if you look at the scientific press or even the popular press, you will very often see something related to this. The latest astronomical research has turned up such and such a peculiar type of planet around another star, and we wonder if there's life there. We've seen something interesting on Mars. Could this mean there is life there? So the quest for life in the universe, in space, is very much a topical thing at the moment. So what I want us to do is to have a look at a few aspects of that search, some of the places where astronomers look, some of the issues involved in what actually we're looking for, what are the signs, and to actually look at what's behind all of it, what's driving it, why is it such a modern obsession? And I believe the answer to that is a very interesting question. And at the end I shall make my own comments on the whole business of looking for life in the universe. I should say that I come to you as a Christian, as a believer in the Bible, as the revealed Word of God. So I make no bones about that. But most of what I'll put in front of you is simply the science related to this, things that are, objective facts in this area, and illustrations to go with it. And I hope that's illuminating and interesting to you. And as I say, it does lead us to consider important questions towards the end. Now, the first question to ask, I guess, is what are the essentials of life? How do we know that what we're looking at is living? And the traditional approach, which is in a lot of textbooks, it's essentially what I was taught at school, is you go through a checklist of what living things are supposed to do. They eat, they excrete, they move around, grow, they respond to changes in the environment, they maintain their internal state at some sort of level of constancy, and they reproduce. So that's one approach. Now, one book that introduces this subject we're looking at, which is generally known as astrobiology, tries to simplify it into essentially under two headings. One, it involves information transmission. So we have the DNA genetic code, and reproduction, which passes on that information to the next generation. And then the other essential that's involved is there is energy disequilibrium. If everything in the environment is in equilibrium, there is no energy source, then you can't have life. There has to be a source of energy for life to take place. So those are the two fundamentals to which this author would boil it down. But I want us to also look at what I believe is an even more fundamental definition or description, if you like, is this word which first came into the literature through two Chilean biologists, Maturana and Varela, in 1973, the concept of autopoiesis. Now, those of you who have a classical education would probably be able to tell us straight away what that means. I'm going to leave it until later. Don't worry about it, but we'll look at the concept of autopoiesis later on as the defining characteristic of living things. Okay, well, being a little more practical, in what conditions can we expect to find life? So these are some of the things that we would that are relevant. First of all, the source of energy, and an organism known as an autotroph would be able to produce, has its own energy source from inorganic materials, inorganic input, if you like. And a heterotroph, we're heterotrophs, by the way, need organic food. It needs to be organic material that we're taking in for energy. There needs, of course, in connection with that, to be a source of the raw materials that are needed for life. In general, it's recognised that we need liquid water, which implies the right temperature and pressure ranges, which we'll look at a bit later. And then there are issues that affect life, temperature, the acidity, the salinity of the environment. And I've just put in a note there, which I will show you some pictures. The extremes that are possible can be demonstrated by creatures known as extremophiles, and an example that's often cited are these tardigrades, and I'll show you some pictures in a moment. And then the other thing that life needs is protection from external damage, for example from solar ultraviolet radiation. Okay, let's just have a brief look at these things called tardigrades. Now these are small creatures. They're a separate order. They're not insects. They're arthropods, a more general classification. They have 4 pairs of these stubby legs with a disc or a pad on the end. They essentially live in water, but they're renowned because they can stand all manner of extreme conditions. Okay, so I've put a couple of those points up there. There's about 400 species known. They grow up to about 1 millimetre long, the biggest ones. They live in water, and you find just about everywhere, puddles, ponds, almost everywhere. But the point about them is that they can stand very severe conditions, desiccation, complete drying out of the environment. Extreme heat, over 100 degrees Celsius. Cold, down to, I think, at least minus 15. Some live in acids, some live in a very strongly saline environment. And their strategy, when exposed to severe conditions that are not very conducive to a happy-go-lucky life, are that they curl up into a ton and they go into hibernation. And the word there is cryptobiosis. And those who would like to find life just about everywhere in the universe are very keen on these things, because they say it suggests that life can exist in all sorts of places that we wouldn't even think of looking in. The fact that there are such creatures as these, there are various other extremophiles that one can cite, such as the bacteria that live in oil fields that are now becoming of interest to oil companies, which years ago we wouldn't have imagined they could exist. But I put the tardigrades in as just an example of that type of creature. Okay, now let's think of looking for life out in the cosmos. What sort of places should we be looking into if we are looking for life? Well, a generally accepted guideline for this is to look for planets rather like Earth. Okay, we know that Earth supports life in great profusion, in great variety, so that should give us a good starter as to where we should look. So, as the second point tells us, it implies rocky planets, large enough to retain a decent atmosphere, and orbiting within a zone known as the habitable zone of their parent stars. And I'll explain this in a little more detail in a moment. The composition in that environment on that planet should provide all the biologically necessary materials. Now, carbon is an obvious one, but that goes along, of course, with oxygen, nitrogen, hydrogen, and then other things like phosphorus, sulfur, iron, and then all sorts of trace elements. As we know, all of these are important to terrestrial life. And then, of course, as I mentioned earlier, the presence of liquid water. If it's in the vapor phase, or if it's solid, if it's ice, and that's it, you're not likely to find life. Okay, habitable zones. Just one or two brief words about these. The star that our putative life-supporting planet is orbiting should be Sun-like. Again, no great surprises there. Brighter, hotter stars in evolutionary terms are too short-lived. They don't sit around long enough, and I'm now giving you the evolutionary view of things, for long enough to support life developing and evolving into any sort of level of complexity. And there's a problem possibly with too much ultraviolet light relative to the visible light. That's particularly relevant if we're thinking about photosynthesis. On the other hand, fainter, cooler stars don't produce enough visible light. Their habitable zones are very, very narrow. There isn't much of a region where your temperatures are in the right range. And they tend to be temperamental. They produce these very large flares every now and again. They're like solar flares, but in comparison to the star, they are vastly stronger, and they could wipe out all life in a single blow, as it were, if they were to occur. What about the orbits of these planets? Well, they should be stable. In other words, they're near circular, as the Earth's orbit is. They shouldn't be disturbed every now and again by another star in the system. Supposing we have a binary system, planets are liable, if they exist to start with, are liable to get ejected and thrown right out of the system, or thrown into a completely different kind of orbit, or even other planets nearby can also disturb them. The inclination of the axis. Earth has an axial inclination of 23.5 degrees, and that's what gives us our seasons. Mars has a similar one, as it happens, but something that's near 0 or 90 degrees tends not to give you the sort of conditions that are conducive to life. And I put in a note here that life on Earth is actually helped by the fact that the moon stabilizes the inclination of the Earth. Mars is reckoned by astronomers. They calculate backwards in time, and they say that it could have flipped over to a much higher inclination and a much lower one at different times, and if there was life, it would change the whole flow of the seasons there. And then the rotation should not be phase locked to the star. Now, I'll explain what that means. That when we look at the moon, we only see one side of it. To see the dark side of the moon, or the other side of the moon, we had to have spacecraft that could fly around the other side. A planet that gets very close to its star that's rotating, that rotation tends to lose energy because of the interaction between them, the tidal effects, until it becomes locked with the same face facing the star. And when you have those conditions, it tends to be very hot on one side, very cold on the other side. And if you have an atmosphere, you have tremendous winds between the two hemispheres because of that difference between the two. It's a very unstable, unhelpful situation. So that gives us a brief bird's eye view of the sorts of conditions we're looking for planets that might hold life resembling what we know. Now, just a brief note here to explain the conditions under which liquid water will be present. This is what's called a phase diagram. Physicists and thermodynamicists in particular use these all the time. People in the oil extraction business are very interested in the phase diagrams of the substances that they're getting out of the ground. But what it shows us, you will see that at 1 atmosphere on the pressure axis, which goes up the left, and 100 degrees C on the temperature axis on the right, there's a line between liquid and gas. So that tells us that at our present atmospheric pressure, water will boil, turn from liquid to vapor at 100 degrees Celsius. Fine, that's when we boil a kettle. Um, if the pressure falls at a lower temperature, it will turn into vapor. Um, if we get below this, what's marked here as the triple point, 0.006 of an atmosphere, then we can't have liquid water in equilibrium. If we suddenly release the pressure on liquid water to a very low pressure, it won't stay liquid. It will either freeze or turn into vapor, depending on whether heat's going in or coming out of it, depending on the exact conditions. So we need an atmospheric pressure above that 6,000th of an atmosphere before we can have any liquid water sitting around. So that kind of gives us an idea of when and where liquid water can exist. And at temperatures below about 0 degrees C, you simply don't have liquid water in the white region to the left. That line there is actually closer to vertical in reality than it's drawn there. You pretty well can't have liquid water at temperatures below 0 degrees C or a bit below that. So that tells you gives you some idea of the conditions we need for liquid water. Now let's have a look at Mars. Mars has attracted a great deal of interest, and as we'll see in a moment, not just from scientists, but just very briefly, there's a regular monitoring of Mars from Earth, and this is just one of those pictures on one particular day recently, and you can see quite a few of its surface features. It's smaller than the Earth. It's just over half the diameter of the Earth. It's a much lower temperature. It's a much drier place. There's no liquid water on the surface. The pressure and the temperature are both too low. So if an astronaut went there and took a cup of water out of the spacecraft, it would turn to ice or vaporize. Some of it would vaporize, some of it would turn to ice almost immediately. You can't have liquid water sitting around on the surface. Just as a sign of the amount of interest that planet has attracted, the NASA website lists 39 space probes that have been launched since 1960. Unfortunately, a lot of those, the Russian ones back in the 60s, all failed to reach Mars at all, and as you're probably aware, some American ones have failed as well. And you may remember the Beagle 2 lander of Christmas 2003, which landed and then was never heard from again. So quite a lot of those have been failures, but that's just an indicator of how much interest that planet has attracted, probably at least as much as everything else in the solar system put together. So why such interest in the red planet? Well, I put at the bottom what I believe is the reason, and it's pretty obvious from all the press releases, that it's the possibility that people see in finding primitive life there, even though, as I've said, there's no liquid water on the surface. Now let's go back a bit to the 1890s, when there was an Italian astronomer known as Giovanni Schiaparelli, who looked at Mars through telescopes, fairly small primitive ones by our standards, and he sketched it, and there are lots and lots of his maps of Mars in sketch form available. There are dozens of these on the web if you wish to look. And he drew them with lots of interesting lines there, straight lines. That's what he saw through his telescope, and he called them canali. Now, I don't speak Italian, but I understand that this word canali means channels. But you can probably understand how it was misunderstood. And people misunderstood it to mean canals, and that implies a civilization that had actually built artifacts that he could see through his telescope. So that in itself caused quite a bit of interest. And Percival Lowell founded the Lowell Observatory in Arizona. And Percival Lowell was extremely interested in that and followed that up in a big way. But you see, there's another aspect to all of this, following on from that H.G. Wells wrote this novel, The War of the Worlds, which came out at about that time. I think it was round about the 1890s that this came out, The War of the Worlds, because he talks about, at the beginning of the novel, it speaks about no one would have thought in the last days of the 19th century. That's the opening phrase, I think, and talking about aliens on Mars coming down to invade the Earth, and you probably know the rest of the story. And my family loved this as a musical, by the way. But that's just one example of the sci-fi that's been generated from this idea of life on Mars, which seems to have started with Schiaparelli and Percival Lowell and people like that. It sort of seems to have a momentum of its own. But let's look at something a little bit more scientific. Now, this was a picture from a press release that came out last year, suggesting that Mars once had a lot of water. And this is based on maps with the gamma ray spectrometer. The Mars Odyssey spacecraft orbited Mars and took gamma ray measurements of different elements on the surface. They each have their own radiation signature. And I think it looked at potassium, thorium, and I can't remember what I think it was iron. And from the distribution of those, they deduced that there was a very large ocean basin, hundreds of kilometers, possibly thousands of kilometers across. And this was the map that was put out with the press releases. And I would suggest to you this is very likely, this is good evidence of an actual ocean covering. We don't know how long it was there, but it looks as if there really was something of an ocean over a very large area of Mars. Now, other evidence of water on Mars relates to the polar caps. Now, these have been known for a long time. Amateur telescopes will show the polar caps on Mars, particularly when it's the local winter season, and they tend to be larger. These are interesting pictures because what they show you is, although you can see it's the same bit of the planet that we're looking at in the left and the right pictures, nevertheless there are some subtle changes going on, and particularly if you look at the patches on the upper right, you will see that the edges of these things are slightly different on these two occasions. They're essentially going from one Martian summer to another, and it's sort of the top center of the picture has changed quite a bit there. The northern polar cap is the bigger of the two. It covers, I understand, something like 800,000 square kilometers minimum, and it gets bigger during the winter season. And that is composed mostly of water ice with some carbon dioxide as well. The southern polar cap, that's in a much more mountainous region, much more rugged terrain, is smaller. It's about 1/10 of the area, so probably about 1/3 of the broad dimensions. And as I say there, it's about 400 kilometers across. But you can see if you look at the surrounding area that the terrain is rougher. The southern hemisphere of Mars is quite different from the northern hemisphere. It's very interesting in its own right geologically because it's very rough, a lot of high altitude terrain, heavily cratered in the south. The north is much, much smoother, and it's a lower altitude in general. So that itself is quite an interesting feature of the planet. Now, a bit more evidence of water. Dozens and dozens of different lines of evidence have pointed to water in the past on Mars. But this is another one that was spotted by the Opportunity rover that started operations there. There was Spirit and Opportunity with the two American rovers that started work there in January 2004. They were meant to operate for a few months. They're still there. They're still sending back data. But this was one of the first places it looked in. It was in a crater called Eagle Crater. They looked at the ground. They had instrumentation there. And they looked and they found these little bluish nodules amongst these rocks that looked like sediments, layers of sediment. And it seems that they are actually layers of sediment, almost certainly laid down in water. But these nodules, they could tell from the surface, the sort of light that was getting reflected back, they could tell that it was hematite, iron oxide was there. And it's often produced by the action of water. But at the same time, the rocks had a high sulfate content. So it had been in a very acidy environment. So there we are, these blueberries, as they call them, formed in an acidic, watery environment. So just another bit of evidence of water on Mars in the past. But as I say, there's no water on the surface. The water that is there is either locked up as ice in the ground, or it might conceivably exist as water underground in a region that receives a bit of warmth from underneath. Now here's something from Mars that has caused quite a lot of interest, and this is a very recent press report which is based on several years of observations from two large Earth-based telescopes. So we have all these space probes, but the Earth-based telescopes, the ground-based telescopes, are still bringing in very interesting results. So these are from the NASA Infrared Telescope Facility and the Keck Telescope, both in Hawaii. For several years now have been looking at the surface of Mars. They've been looking at the reflected sunlight, and they've looked for absorption lines in that sunlight. Now an absorption line is like a signature that an element leaves on the light. Now stars have absorption spectra because elements in their atmospheres absorb light at very particular wavelengths which are peculiar to that element. It's like its signature. And if you can identify the wavelengths or the pattern of wavelengths that are missing, you can identify the element responsible. Well, the same is true here. You look at the surface where there's reflected sunlight, you check where the dark bits are in your spectrum, and that's like a signature of the materials that are there, and it's the molecular spectrum of methane is producing absorption. And on the left here we have an absorption map, if you like, the red being where a very strong absorption, and the blue where virtually none at all, so it's shaded like any other contour map. And on the right we sort of have a map of the geology of that area in terms of the minerals. Now, of course, the press got very excited about this because they said, well, of course, it could well be living things under the ground are producing methane, because life tends to produce methane, and it's coming up out of the ground, and it comes out in a plume that moves in a certain direction. Now, with all the detection of methane on Mars, there have been other detections. This is probably the most solid because it's based on several years of observations. There are always other possibilities for explaining the origin. So there are geological effects which could be producing it, natural effects which don't involve life. The interesting thing is that when you read the press reports, they talk a lot about the life possibility before they get onto the other possibility. They always do it that way round. And one report I've seen in Sky and Telescope, the American popular astronomy magazine, says, don't we all wish it to be life? In other words, never mind objectivity, we all want it to be life that's producing this because we want to find life, of course, is the implication. Right, now, if you were following the scientific press and other press back in the 1990s, you may have been aware of this, which caused quite a stir, which was a meteorite found in Antarctica in 1984, which in the 90s was examined very carefully. Its mineralogy was examined very carefully, its crystal structure, its surface, what had changed on its surface, and everything was looked at very carefully. And one team of investigators came out with a conclusion that it likely had signs of life on it. Now, first point I should make is that this almost certainly does come from Mars. Earth has a stronger gravity than Mars. We're nearer the sun, which means the sun's gravitational field will tend to pull things floating around Mars towards Earth more than allowing them to move in the other direction. And there's a number of meteorites that have been identified as having a Martian origin. Either there was a volcano, a very powerful volcano, or there was an impact from a meteorite or a comet or something on Mars which threw up material so violently that it got flung into space. And that could have ended up on Earth as a meteorite. So it almost certainly is from Mars. And that identification comes from the gas composition built into that meteorite when it was analysed. But what really hit the headlines was this picture at the bottom, which appeared actually in Time magazine. I remember seeing Time magazine in 1996, and there was some headline about, is this Martian life? And you can see that little worm-like feature in the middle there, which many people thought was a remnant bacterium. In the end, the consensus, after a lot of arguing, after a lot of papers were written, and indeed some bad tempers, it was decided that it probably didn't represent life. It was much smaller than any known living cell. Its length was 100 nanometers. So it's so much smaller than anything we know that they could hardly call it life, and there wasn't really anything else to support that notion. But certainly that story had quite some currency, and I think people would look at any other Martian meteorite with great interest now to see if there are any further clues in that direction. Now I'll move on to the other places in the solar system that people have looked at as a possible location for finding life. And the first of those, I've only got two of them, is Europa, which is the second Galilean satellite of Jupiter. It was discovered, the sequences going outwards from Jupiter, Io, Europa, Ganymede and Callisto. And you can see them in binoculars. If you look at Jupiter with a pair of binoculars, you can see those four. It's the second in line. It's the smallest of the four. And there's a picture, there's a frame there, I think, from the Galileo mission with Europa standing in front of Jupiter. There's a close-up on the right there. You can see that it's a very fractured sort of surface. There's a lot of ice on that surface. And if you look in detail at the fractures, and the spacecraft, this has been done from a number of spacecraft, but particularly Galileo, you appear to have fresh features there. So the suggestion is that it's resurfacing itself regularly. And the picture on the lower left, that's a false color picture, but it's an idea. It's meant to give you an idea of different chemicals on the surface. It's a very strongly oxidizing environment there, but you'll also see streaks going from upper right to lower left, which is where the ice seems to have fractured and reformed. Now the suggestion is, in connection with life, all right, you can't have living things sitting on top of that. It's much too cold. It's a very hostile environment. but clearly there is some melting going on underneath. Now, Europa has heat coming out from inside because the tidal effect of Jupiter warms it up. Now, it's known that Io, which is closer in, is volcanically the most active body in the solar system. It's quite spectacular, the volcanoes that it pushes out. And when I think it was the Voyager spacecraft went past Jupiter, everyone was wowed by these pictures of these massive volcanoes. Now, that's generally believed to be a result of the tidal forces within the planet induced by Jupiter that heat it up and send out these volcanic plumes. Europa, that mechanism is supposed to operate at a much lower level, so there is some warming going on, and it's reckoned that there is an ocean underneath the ice. And if you look at the picture on the bottom right, these are artists' conceptions of two possible scenarios. The one on the left where the ocean is fairly deep, you get plumes coming up, convective plumes coming up and warming it and breaking it every so often. And they suggest there could be an environment for life down there. And the one on the right where you've got a very thick layer of ice, but it actually circulates itself very slowly, and the heat comes up by convection actually within the ice. But people are now seriously suggesting sending a probe to Europa to burrow down through the ice and to try and put some sort of submarine unit down there to have a look to see if they can see any creepy crawlies down there. And that is a serious suggestion, okay? Titan, that is the largest satellite of Saturn, and you can see in the picture on the top left that's Saturn from the Cassini spacecraft, and I think Titan is the one towards the upper right. It's the second largest natural satellite in the solar system. It has a thick atmosphere. A natural colour view on the upper right there will show you this orangey sort of smoggy picture. There's actually a lot of structure. I can't tell you exactly how that picture on the bottom left was taken, but you can see there's a lot of layering there. This was a spacecraft that was close up, looking in the right wavelength range, and you can see a lot of layering in the atmosphere there. Now, it's essentially a methane atmosphere with some nitrogen there. I think there's some carbon dioxide. But when they sent the Huygens spacecraft down there, I think that was January 2004, it actually landed on the surface and took pictures. And remarkably, it looked like Earth in the sense that you had lakes and oceans and mountains and all this sort of thing. And there was obviously a hydrological cycle going on there, as on Earth, except that they decided it was liquid methane. And the solid was all ice. And the picture on the bottom right gives you some sort of glimpse of what it looked like at the right wavelengths that penetrate, but from a distance as a spacecraft is coming down. But the temperature there is at about minus 179 Celsius. Doesn't look very favourable for life, but again, some suggest that it shows us the conditions in the primitive Earth. It has the right mix of potential biological molecules there, and therefore we can learn much about the origin of life on Earth by studying Titan. And some have said, well, if you sort of drill right down, it should be warmer, and therefore there might be a layer of liquid water. There might be extremophiles that have developed there. So they go, quite an extreme environment, but they suggest there could be life. Let's have a think about organic materials on meteorites, because these these attract quite a bit of interest. And I'll focus on one that has attracted most. It's sort of typical but rather special in a sense. The Murchison meteorite that landed in Australia 1969 is known as a carbonaceous chondrite, which means it has these little round things in it which called chondrules. That meteorite has been found by careful study to contain lots of organic molecules, that is nucleic acid bases, fatty acids, and a whole lot of amino acids. But I note that only 6 of those have ever been found in terrestrial life. Most of them have no relevance to terrestrial biology. Now, an analysis was published in the 80s which showed the presence of both forms of the amino acid. Now, technically, according to the literature I've seen, these are called enantiomers, so they are effectively left and right-handed forms. My right and left hands are essentially the same, except that they're mirror images. They're not the same in terms of handedness. Now, this is the same with these amino acids. You have both enantiomers. That's not true in terrestrial life. Amino acids come in the left-handed form, and I believe that that's exclusively so, and that's an important aspect of biology. But on this meteorite, you had both forms. The interesting thing was that there was an excess of the left-handed form of amino acids, so there was a lot of fuss in the literature about this, a lot of arguing. But I think it's fair to say that the issue of contamination with terrestrial material had not been fully taken into account, so that what you should do if you really want to sort of catch what was on the meteorite itself, you have to check the soil in the area where it landed as soon as you possibly can after the fall, because otherwise all sorts of things can happen on the surface, which mean you end up with materials of terrestrial origin getting into the rock, and that will then mess up any measurements on the meteorite itself. So it seems quite likely that there is contamination with earth-based amino acids mucking up those measurements, so we probably shouldn't get excited about it. Now, I put this picture in because I think this is one of the most amazing comets. I didn't actually see this. I had one opportunity, January 2007 it was around, and unfortunately I was in a meeting at work at the one time I might have seen it. So the Aussies had the best chance, and the Aussies took those chances. They got some fantastic photographs. This is Comet Mach-Naught, or technically C/2006 P1. But I just put it there as an illustration of the idea that comets might have brought life from space to Earth. They have a lot of organic molecules, pretty simple ones, but lots of them have now been found on comets. And occasionally in the past they've collided with the planets, including Earth. So the question arises, could life have reached Earth from space? And that leads us on to this idea of panspermia, life from space. Now, as I put there, and Paul would, I trust, verify this, panspermia is Greek for seeds everywhere. And again, no surprises. The idea originated with the Greeks, and the writers that have been quoted in the literature I've seen are Anaxagoras and Socrates. The 20th century version, that is broadly the paradigm followed by the followers, is the Oparin Haldane paradigm, but there wasn't a lot of interest in that until the 70s, when Fred Hoyle and Chandra Wickrama Singh came up with this idea, which revived it, based on the organics in interstellar dust and comets, that because interstellar dust contains a lot of basic organic materials, comets certainly do, we know that meteorites do, they made this proposal that not only that, but whole cells that arose elsewhere seeded life on Earth. And I just note in brackets here that part of the reason for this idea coming up was that Hoyle considered that Darwinian evolution was inadequate to explain the origin of life. And the other aspect here of panspermia in its modern form is James Lovelock's Gaia hypothesis. His book on Gaia was published in the 70s, and he viewed the Earth as an organism with a tendency to produce life from within itself. But I note there that this has pantheistic elements in it. There's a strong element of that if you read in depth. Now, according to this webmaster Kleiss, in the title he now gives to the idea, Cosmic Ancestry, he makes this interesting comment that life can only descend from ancestors at least as highly evolved as itself. In other words, he's giving up on explaining life starting from scratch. He's saying, well, it just came from somewhere else. It was already well evolved, and then it came here. So he's kind of giving up on trying to explain where life came from. Okay, let's move out beyond the solar system now. And I'm going to talk for a few moments about exoplanets. The first generally recognized exoplanet was discovered by Mayer and Kalos in 1955, the star 51 Pegasi. It had a variation in its spectral lines. I said earlier that a star has spectral lines, bits of its spectrum that are missing because they've been absorbed in its atmosphere by certain elements. Now, those lines are at definite wavelengths, but if we watch them carefully over a period of time, in some cases they move from left to right. They move to longer wavelengths and then shorter wavelengths, and if they do this on a regular basis, it's telling us that something is going on. Now, if we interpret that as another body moving round it, pulling on it and giving it a periodic push and pull, such that it's moving sometimes towards us, sometimes away from us, we're getting a Doppler effect. It's shifting the wavelength up and down towards the red, towards the blue. And so, having observed these very subtle variations, but on a periodic basis, they deduced that there was a body moving around this star with a mass of about half that of Jupiter, and that was the first recognized exoplanet. Now, since then, lots more have been discovered, and the official website, which I looked at last week, said that to date we have 340 of these objects now accepted and catalogued. Some that were claimed in the early days have now been rejected because of instrumental errors in reducing observations, all sorts of things like that. But these are ones that have been accepted as real discoveries. Now, what methods are used? Point number 2 here. Radial velocity, that's the one I've just mentioned to you. The large majority of these objects have been discovered by this radial velocity of the star changing through the Doppler effect. We can detect that, measure it, and we can deduce not actually the mass of the planet, but the minimum possible mass. We're looking at the projected orbit as we look at the sky. So it tells us the minimum. The mass could be larger if its orbit is tilted. But that gives us a minimum possible mass for that object orbiting the star. And something like 300 of those have been discovered by that route. Another one is transits. And this is where the planet goes in front of the star and blocks out a teeny bit of its light. And if we have an instrument that is accurate enough, sensitive enough, we can actually detect that drop in the light level. And if it occurs periodically, we can tell the orbital period of that planet, and we can work out lots of other things. We can actually work out its mass if we have a radial velocity measurement as well. And I think something like 30 or 40 are known now in that category. A lot of them were already known by radial velocity, but are now also known through transits. Another one is microlensing, where the planet actually affects the light from the star for a moment, and you get a characteristic light effect which can be interpreted as the presence of a planet. There are just a handful in that category. There's timing. Really the first one was discovered in 91, but that was around a pulsar, so it couldn't possibly have held life. It was very small, and it was detected through changes in the timing of the pulsar. And then the last one is direct imaging, and I'll show you some direct images where we can actually image the planets directly. Now, what sort of pattern is emerging with these exoplanets? Generally, they are Jupiter mass or larger, so they're pretty big. They're orbiting quite close to the parent stars, and the orbits are nearly circular. Now, that's actually a problem for the theorists, because if you go to the theory of how the solar system formed, you don't get big planets forming close in. It doesn't happen. The dynamics are all wrong. So as soon as they came up with this conclusion, we got Jupiter mass, big planets, close to the star. Whoops, we have to think of a way of producing them. So very quickly, lots of new theory came out as a result of this finding. The other point is quite a few are smaller, lower mass, and they have much larger orbits, but they tend to be very eccentric. In other words, they're very oval shaped. They spend a lot of time away from the star and then come in close very briefly. Those certainly wouldn't be good if you're looking for life. The other point is here, there's very often a lot of dusty, rocky material. We can see that from the infrared emission from these systems. Sometimes we can image that infrared material. And for a system that's long since developed planets, that stuff shouldn't be there. But I note at the bottom here that we've found nothing remotely Earth-like to date. But that's what they would really like to find. Just to show you some statistics, at the top there we're plotting, and this is again from the official exoplanet website, so this is sort of right from the horse's mouth. We're plotting the size of the orbit along the horizontal axis and the mass of the planet along the vertical axis, and I'll try and move the pointer along to give you an idea. This line here is about a Jupiter mass along that line there. So a lot of these are bigger than Jupiter, even up to 10 times bigger in mass. Some are below. The Earth would come at about this level on the graph. The one point down right at the bottom is one of those planets I mentioned near a pulsar, so it's not relevant if you're looking for life. If you look at the bottom plot, we're plotting there, again along the x-axis, the size of the orbit, the semi-major axis as we call it. And sorry I didn't explain this, but an AU is an astronomical unit, which is the distance of the Earth from the Sun, so that's our yardstick for that horizontal axis. And that's one astronomical unit there. And what you'll see is that the eccentricities can go very high. Now you can't get a bigger eccentricity than 1. That means an ellipse that's very, very elongated is an eccentricity nearer to 1. Most of the solar system is near circular. It's right down in this bottom region. But you see those that have a bigger orbit, a larger semi-major axis, tend to have a very high eccentricity. That's not helpful at all if you want to look for life. Now I'll put some notes here. The Earth's mass is 1/318th of the mass of Jupiter. The size of Jupiter's orbit is 5.2 astronomical units. It's 5 and a bit times further away than the Earth is from the Sun. If you have the same composition as the Sun, metallicity, it's only a planet up to 13 times the mass of Jupiter. Otherwise you're talking about brown dwarfs, a sort of nearly failed star. We're talking about a different class of objects then. If a planet comes in very close, tidal effects mean it tends to go circular very quickly and it tends to get phase locked. And I said before that if that happens, that's very bad for any potential life. But at the bottom there I said just about all of them have masses that exceed the mass of the Earth. They're all pretty massive. Now here's a couple of images that were released together last November, which are direct images of extrasolar planets. It's the first ones. The one on the left was taken from the Hubble Space Telescope, and you have to look at the inset to see that funny little blob there, but that is actually an image of an extrasolar planet, because they already knew there was one there from the radial velocity studies. They did a lot of very clever masking of the starlight in the telescope so it didn't swamp the picture, and they were able eventually to clean up the picture electronically enough to spot the planet. So there we are. That was Hubble Space Telescope. The one on the right was released at the same time, and it's a system, in fact, with 3 planets in it. There's only 2 of them on that picture. That's a better picture than, it's the best to look at out of the set, but there's actually 3 planets there, and they were all imaged, and this is by the Gemini telescopes we used for this one. So we're now into the realm of actually imaging these things directly. This is the technology that's come to fruition within the last year. We're moving forward in terms of exoplanet observations. This is an example of the light changes you can get with an exoplanet transiting in front of a star, like eclipsing it, but only in a very, very limited way. And the observer responsible for this is somebody I've met, someone I've corresponded with quite a bit. He's an amateur. He lives in Belgium. He's quite an electronic whiz kid. He knows a lot about telescopes as well. He uses a CCD camera attached to his telescope, and he produces data for what's called the Centre for Backyard Astrophysics, which is organised by Professor Joe Patterson at Columbia University, who has a network of amateurs and professionals all across the world, which he gets to observe a particular object all at the same time. So you've got lots of observations of the same thing from different parts of the world, and you can get some very useful results that way. And this is one that he took back in 2004, and you can see the light curve dipping by this amount, and it's quite a clear eclipse. They're not always as clear as this, but that was a very nice piece of data which Tony put up on the web. So you get an idea of what they're doing. You can see this dip. It recurs periodically, and that tells you there's an exoplanet there. If you've measured radial velocities as well, then you've got data on the size of the planet's orbit, its mass, and you also know something about its physical size because of the amount of light it blocks out, and you can say then something about its composition. If you know its mass and its size, you're starting to say quite a bit about it. So there's more information coming in this direction. Now, moving off on another tangent perhaps, but it's all in this broad area of looking for life in space. I don't know if you watched E.T. My wife thinks it's quite a nice film. And this is another alien picture on the right. I don't know if it's from a particular film. It's just one of those images that we're probably all used to. Interesting to me that when we come up with aliens in a science fiction context, they all have very strong similarities to humans. They have a head, 2 eyes, a body, 2 arms, 2 legs, mouth. A few things might be a bit peculiar or a funny colour or something, but basically they have a humanoid structure. We couldn't kind of relate to them, I think, if they weren't. But I'm asking now the question, is there any reality to this popular idea of an alien along standard sci-fi lines. Okay, what are the questions? Is ET ever going to phone home? How much searching do we need to do to find extraterrestrials? And if we're seriously looking, what sort of signals could we expect? How would we know if we'd had a signal? If they sent us a message, would we know it's a message from them? And what sort of communication could we have? And then a question I put in there at the bottom. I don't particularly want to discuss this. This harks back to Eric von Däniken and his idea that God was an astronaut. It's interesting that he was in prison for fraud when he wrote that. But there's quite an empire has been built up on the royalties he's made over the years. And it has strong occult connections, in fact. But it's a question that one might ask. Well, I'll offer just a little bit of science in this broad area where we're getting slightly more serious here. And everyone interested in trying to contact intelligent life in the universe will refer back to this Drake equation. This is written down in 1961 by Frank Drake, who was very interested in making contact with extraterrestrials. And basically it says we've got all these factors, and this will tell us how many communicating or communicative civilizations could we possibly communicate with. And you can see the factors there. How fast suitable stars form, how many of them have planets, how many of those planets are Earth-like, how many of those have life developing, and of that, where life develops, how much of it is intelligent, and what fraction of the intelligent ones bother to communicate through electromagnetic waves. And then there's the lifetime factor comes in, and you notice some of those things astronomers reckon you can put a serious number on them, but others it could be zero. We simply don't know. In other words, it is quantifying our ignorance, if you like. That's one way of looking at it. Others would say, well, we're filling in the gaps. The numbers are hardening up. We can make predictions. The interesting thing is different authors come up with totally different numbers. I think Frank Tipler has come up with a 0. Others have come up with multiple billions. So it depends who you ask. But the simple fact is they've been looking seriously since 1960. No confirmed messages have been received on planet Earth to date. You can actually take part in this if you wish. You can have your computer, when it's idling, actually process data for them. SETI at home, it's called. If you sign up for that, you can take part in looking for extraterrestrial life. Personally, I think it's more worthwhile to process data looking for involved in cancer research. But anyway, that's a choice. Okay, now what I'm asking now is what motivates people who are interested in astrobiology. What's actually behind it? Because it's a very strong drive in the media. What's motivating it? Well, in the past there was lots of speculations. William Herschel, the astronomer who was actually a Christian, who discovered the planet Uranus, he thought there were people living on the sun. But all of that kind of thinking was just speculation. Now what we find is there's usually a very Darwinian theme. Darwinian evolution comes in somewhere along the line, and it's very prominent. And the Beagle 2 lander on Mars in 2003 is an example, referring back to Darwin's Beagle voyages, of course. Another one looking for terrestrial planets, which is planned, was originally called Darwin, due for launch in 2015. I think it's now going to have another name. And I think you can read what the roadmap here suggests. These questions: how does life begin and evolve? Does it exist elsewhere? What's the future of life on Earth and beyond? And then the bit at the bottom, which is another bit, and I believe I'm quoting in context here, exploiting the universal laws of physics and chemistry to understand polymer formation, self-organization processes, and so on, and Darwinian evolution that might lead to the emergence of life. Now I'm quoting, to my mind you can't have Darwinian evolution until you've got life. But anyway, let's just leave it like that. That is a quote. Fundamental assumptions. The assumption seems to be that life begins spontaneously by self-organization amongst primordial chemicals. A spontaneous origin for life is likely wherever suitable conditions exist, and it then develops by a process of Darwinian evolution. But I would ask, how well established are those assumptions? And I first make the point that the spontaneous generation of life was falsified by Pasteur, whose name is attached to even today to pasteurized milk. And I would just point out that we don't know of any counterexamples. Second point, chemical self-organization occurs on a limited level, but never generates biologically relevant information. That might be a point you may wish to discuss. Observation and information theory both imply that complex specified information, such as characterizes life, always tends to degrade. That's the direction in which it changes. So it must have been there from the beginning. Now I'll try and formalize that by going back to this concept of autopoiesis. It's the concept of self-making. All known life possesses this characteristic, this property, the ability to make use of the environment in terms of materials and energy, to survive and to propagate itself into the future. And I'd also like to mention this concept of a Pollyannian impossibility. This dates to the science philosopher Michael Polanyi, 1968. Basically, the idea that you can't reduce a structure into its component parts. Now, examples that I've seen: a silver coin, written text. To have a piece of paper with written text here, I can analyze the ink, I can analyze the paper, how they were made, and tell you to the nth degree what's there and how it came to be. That doesn't give you the message that's written down in the words. They're imposed separately from a different level. So he's saying that you can't derive this level from this level that it depends on. That message depends on a medium. It depends on the paper and the ink. What you see on the screen depends on the electronics and the properties of light. But those themselves will not give you the message. That has to be put into that medium. So the impossibility is going from the lower to the higher. And the argument here is that life has this autopoietic hierarchy built into it. First of all, biology needs a pure composition to its components. If you have an amino acid with the wrong handedness, it won't go, it won't have it. And all the evils of the thalidomide drug, I believe, were a result of that you had a mixture of the handedness of the molecules that were in there, and it meant lots of babies were born deformed. You need pure composition. Single molecules have to be right for life to make use of them. That doesn't happen naturally in the chemistry in the world out there, which is dirty, messy, and you always have mixtures. You have components with a highly specific structure. Enzymes in cells have a very, very well-defined role. They can speed up reactions by billionfold and more because they have a very specific structure, very specific activity, and the water in a cell has a structure that has to fit in with all the recognize biological molecules, otherwise the whole thing doesn't operate. The structure has to be very specific, but you can't derive that structure just from the composition. It's a higher level of organization. Then at a higher level still, you have functionally integrated components, so ATP synthase, and you can see wonderful videos of that on the web, of this little motor that produces the energy coinage for the cell, the ATP, when you drive it in one way. When you drive it in the other way, it uses that for some other purpose. It's a two-way thing. That's an integrated bit of machinery built into the cell, which doesn't derive just from knowing the structure of the molecules there. It's a different level of organization, but it's necessary for life. It's there in all life. At a higher level still, all of these machines and bits and pieces are regulated by information-driven processes. So we have the DNA and bits that switch on and off at different times. That regulates very precisely what goes on. That's a higher level again. And then what I've called an inversely causal survival strategy based on meta-information. All right, big words. What that means is that there's actually an anticipation of future need. We think of cause and effect by the cause happens now, the effect is something that happens later. But this is inversely causal in the sense that something happens now in a biological organism because of an anticipated need in the future. Examples. One given in the evolutionary literature is that of a stegosaur embryo will actually start to develop the bony plates for the animal's back. It won't need them until it's an adult. It certainly doesn't need them as a juvenile. The same would be true of the little group of cells that's always present in the body of a butterfly larva, a caterpillar. While the caterpillar is happily munching away and growing, it doesn't need them. But when it pupates, its body structure breaks down, and then that little bag of cells that was there right from the beginning takes over and molds it into the body of the butterfly or the moth. And that, of course, is the adult animal that emerges later. It's needed for that stage, for its reproductive stage. And of course, the reproductive organs of any creature that reproduces sexually are not necessarily needed for survival of the individual. They're only needed later on in life for the propagation of the species to the next generation. So it's an anticipated need, as it were, for the next generation. And what I'm saying is that all life possesses this hierarchy of levels, if you like, of things that are built on lower levels, all completely different from the messy chemistry, mixed up chemistry that you have outside and can't be derived from it. So I would suggest to you that that implies that life cannot have the naturalistic origin that's presupposed in this search for life in space. Okay, what's the state of play? We're nearly finished now. We haven't detected any extraterrestrial life that's been confirmed anywhere. We haven't detected any signals in the SETI program, the search for extraterrestrial intelligence. The origin of life is still a great mystery, and I would argue that a naturalistic origin is an impossibility, and I would suggest to you the autopoiesis as a very good reason for saying that. There are problems that one can throw up concerning Darwinian evolution. The tree of life has recently been questioned in New Scientist. There are big issues there. Genetic entropy, the degradation of the genome, is something that suggests it can't really operate as it's meant to. And yet, astrobiology seems to be a growing interest, and it's a big driver in space exploration and astrophysics research. It's the reason for almost every big spend that anyone wants to make in the next few years. And it's widely assumed, at least in the press, that finding extraterrestrial life is only a matter of time. It's bound to be there somewhere, guys. And I thought it's worth reflecting on these 2 years, 1953 and now. Watson and Crick in 1953 announced the discovery of the DNA helix. Urey and Miller, they created amino acids by passing electric current through a reducing gas mixture. They put ammonia, methane, hydrogen and water together, and they managed to produce amino acids. But will you note that they produced a lot of goo, and they were both handed forms of the amino acids. Fast forward to 2009, the science of genetics is a huge growth area. We could hardly a day passes without people referring to genetics. It's got tremendous applications in medicine, forensic science, so on and so forth. That's where DNA has led us. Origin of life science has gathered lots of speculations, but it really is still a huge mystery. And astrobiology, despite great media interest, burgeoning research effort, it has yet to discover a single instance of its subject matter. So I would argue, in conclusion, that the irreducibly complex autopoietic nature of all known life rules out a naturalistic origin. You may wish to query or to discuss that, but I put that to you. And I would suggest that there can be no extraterrestrial life to discover unless an intelligent designer has put it there. Now, as I read the Bible, it suggests that God created the earth, and nowhere else comes into the category with it, to be inhabited. Genesis 1 makes that very clear, that he created the heavens and the earth, and then it describes how the earth was filled with living beings, with man as the crown. But he did it deliberately, and it was the earth. It was tohu wa vohu at the beginning. It was without form and void. And filling it with these creatures was how God changed that. That was how it's meant to be. And Isaiah tells us the same. He made the earth to be inhabited. But it's quite clear it's in the context of the heavens and the earth. Nothing else is mentioned. So it's a very old-fashioned view, if you like. It's one that people love taking pot shots at, but I would say that is what the Bible suggests, that the earth is the place he made to be inhabited, and therefore I do not think that he created life elsewhere. So I'd make this prediction, and this is a falsifiable prediction, okay, that no genuinely extraterrestrial life will be found. Now, why I put in the word genuinely is that it is conceivable that a meteorite from Earth carrying some primitive form of life with it could have landed on Mars, and it could conceivably have survived. But that is kind of the only exception that would fit in with that view that I'm offering to you. But I would also say, as I say here at the bottom, watch this space. Keep watching what gets discovered. Keep watching the press announcements. Keep watching, keep following, because a lot is happening. A lot of research is going on. And I think we should take an active interest in it, because it's kind of the cutting edge of the issue of whether life really did start by the naturalistic origin that we're told in the media repeatedly, and especially in Darwin year. This is drummed into us now, and it seems it's almost psychologically necessary for those who believe that to find life out there, because it would kind of prove that despite all the arguments, after all, it did happen by itself. That would, in their minds, I think, produce that conclusion. So watch this space. Keep watching. I may be proved wrong. It's open to falsification, but I would make that prediction that we will never find genuinely extraterrestrial life. And I'll leave you with a picture of the place that we all know does hold life in a wonderful and teeming variety. But that's essentially the material I had for you. cryptobiosis. And those who would like to find life just about everywhere in the universe are very keen on these things, because they say it suggests that life can exist in all sorts of places that we wouldn't even think of looking in. The fact that there are such creatures as these, there are various other extremophiles that one can cite, such as the bacteria that live in oil fields that are now becoming of interest to oil companies, which years ago we wouldn't have imagined they could exist. But I put the tardigrades in as just an example of that type of creature. Okay, now let's think of looking for life out in the cosmos. What sort of places should we be looking into if we are looking for life? Well, a generally accepted guideline for this is to look for planets rather like Earth. Okay, we know that Earth supports life in great profusion, in great variety, so that should give us a good starter as to where we should look. So, as the second point tells us, it implies rocky planets, large enough to retain a decent atmosphere, and orbiting within a zone known as the habitable zone of their parent stars. And I'll explain this in a little more detail in a moment. The composition in that environment on that planet should provide all the biologically necessary materials. Now, carbon is an obvious one, but that goes along, of course, with oxygen, nitrogen, hydrogen, and that are, objective facts in this area, and illustrations to go with it. And I hope that's illuminating and interesting to you. And as I say, it does lead us to consider important questions towards the end. Now, the first question to ask, I guess, is what are the essentials of life? How do we know that what we're looking at is living? And the traditional approach, which is in a lot of textbooks, it's essentially what I was taught at school, is you go through a checklist of what living things are supposed to do. They eat, they excrete, they move around, grow, they respond to changes in the environment, they maintain their internal state at some sort of level of constancy, and they reproduce. So that's one approach. Now, one book that introduces this subject we're looking at, which is generally known as astrobiology, tries to simplify it into essentially under two headings. One, it involves information transmission. So we have the DNA genetic code, and reproduction, which passes on that information to the next generation. And then the other essential that's involved is there is energy disequilibrium. If everything in the environment is in equilibrium, there is no energy source, then you can't have life. There has to be a source of energy for life to take place. So those are the two fundamentals to which this author would boil it down. But I want us to also look at what I believe is an even more fundamental Okay, well, thank you very much, Paul, first of all for the invitation to come here and for the introduction, and thank you for everybody who's turned out. The subject I'm going to address tonight is the quest for life in the universe. And if you look at the scientific press or even the popular press, you will very often see something related to this. The latest astronomical research has turned up such and such a peculiar type of planet around another star, and we wonder if there's life there. We've seen something interesting on Mars. Could this mean there is life there? So the quest for life in the universe, in space, is very much a topical thing at the moment. So what I want us to do is to have a look at a few aspects of that search, some of the places where astronomers look, some of the issues involved in what actually we're looking for, what are the signs, and to actually look at what's behind all of it, what's driving it, why is it such a modern obsession? And I believe the answer to that is a very interesting question. And at the end I shall make my own comments on the whole business of looking for life in the universe. I should say that I come to you as a Christian, as a believer in the Bible, as the revealed Word of God. So I make no bones about that. But most of what I'll put in front of you is simply the science related to this thing, definition or description, if you like, is this word which was first came into the literature through two Chilean biologists, Maturana and Varela, in 1973, the concept of autopoiesis. Now, those of you who have a classical education would probably be able to tell us straight away what that means. I'm going to leave it until later. Don't worry about it, but we'll look at the concept of autopoiesis later on as the defining characteristic of living things. Okay, well, being a little more practical, in what conditions can we expect to find life? So these are some of the things that we would that are relevant. First of all, the source of energy, and an organism known as an autotroph would be able to produce, has its own energy source from inorganic materials, inorganic input, if you like. And a heterotroph, we're heterotrophs, by the way, need organic food. It needs to be organic material that we're taking in for energy. There needs, of course, in connection with that, to be a source of the raw materials that are needed for life. In general, it's recognized that we need liquid water, which implies the right temperature and pressure ranges, which we'll look at a bit later. And then there are issues that affect life, temperature, the acidity, the salinity of the environment. And I've just put in a note there, which I will show you some pictures. The extremes that are possible can be demonstrated by creatures known as extremophiles, and an example that's often cited are these tardigrades, and I'll show you some pictures in a moment. And then the other thing that life needs is protection from external damage, for example from solar ultraviolet radiation. Okay, let's just have a brief look at these things called tardigrades. Now, these are small creatures. They're a separate order. They're not insects. They're arthropods, a more general classification. They have 4 pairs of these stubby legs with a disc or a pad on the end. They essentially live in water, but they're renowned because they can stand all manner of extreme conditions. Okay, so I've put a couple of those points up there. There's about 400 species known. They grow up to about 1 millimeter long, the biggest ones. They live in water, and you find just about everywhere, puddles, ponds, almost everywhere. But the point about them is that they can stand very severe conditions, desiccation, complete drying out of the environment. Extreme heat, over 100 degrees Celsius. Cold, down to, I think, at least minus 15. Some live in acids, some live in a very strongly saline environment. And their strategy, when exposed to severe conditions that are not very conducive to a happy-go-lucky life, are that they curl up into a ton and they go into hibernation. And the word there is